Will this be the last carbonyl video? I don't know. Probably not. I love talking about carbonyls. I can't shut up about them. So there will probably be more, but we're getting close. We're almost through. We're almost covered an entire chapter. So we're continuing on to talk about carbonyl reactions and how do we convert between when we use carbonyl substitutions, what are the things that we look for, right? So one of the things we look for is on the waterfall is how good is our leaving group? Because if our leaving group is a really good leaving group, we can convert that leaving group into almost anything using substitution. If our leaving group is a bad leaving group, then our options are a lot more limited, right? If we have an amide, so if we're at the bottom of our waterfall, excuse me, if we're at the bottom of our waterfall, right, and we want to convert an amide into something else, we're a little bit stuck as far as carbonyl substitution goes. What we need is kind of a get out of jail free card. How do we work around that problem of having a bad leaving group? And the answer is we have a carboxylic acid. So carboxylic acids are kind of held off to the side of this waterfall diagram. So instead of all the things that go down, you'll notice on the carboxylic acid side, these arrows kind of go both ways. We can convert an ester to a carboxylic acid. We can convert an amide to a carboxylic acid. Same with anhydrides, same with acid chlorides, but we can also convert a carboxylic acid into all of these things. Right? And we'll talk a little bit about how we manage that here in a moment. So first of all, one of these we've actually already done. If you have a carboxylic acid and you want to make an anhydride, of course, all you have to do is just react it with an acid chloride. This is technically a reaction that we've already talked about. This reaction here and this reaction here are the same thing. We have two different starting materials there. So that one's kind of trivial, so we're not going to talk about it very much, but you should definitely draw out that mechanism and think about it. All right, so first of all, acid chloride to carboxylic acid is a pretty straightforward one. We want to replace the chlorine, we want to add an OH group, and so of course we would just add something like H2O. You might need to add H plus, or you could use sodium hydroxide and have an OH minus, right? Either one would work. So you could use this set of conditions, H2O, H plus, or you could use sodium hydroxide. Right? Either one will substitute the chlorine with the carboxylic acid. So that's pretty straightforward. If you want to convert an ester to a carboxylic acid, you can also, again, use H2O and H plus. This is very similar to, right, this is just another substitution reaction. Only what we're going to do here, this is very similar to the acetal stuff that we did. I lost my marker. There we go. Right, if we have an ester and we react it with H2O and H plus, right, where we're going to get, so H2O will add in and we'll end up at this kind of intermediate where we have this, right? Now, when we add H plus to this H plus can go a variety of different places. It can make the OCH3 into a leaving group, or it can make the OH into a leaving group, right? And both things will happen. If we make the OH a leaving group, it goes back to the ester. If we make the OCH3 a leaving group, it goes to the carboxylic acid. And so the way we cheat this system is we have a whole bunch of water around so that if it goes back to the ester, what happens to the ester is water will add back in and we'll end up back here. Right? And so we kind of bias the system so that even if we make the ester, we always end up here. And eventually, all the H pluses will end up on the OCH3, and we kind of cheat the system and end up with this as our good leaving group. This is now our best leaving group, and so we're going to always get to the carboxylic acid, right? Once we lose H plus, gives us our carboxylic acid. So that works great. We can add H2OH plus to an ester and get to the carboxylic acid. This actually also works for the amides. And again, this is one of those where you cheat a little bit and just kind of flood the entire reaction with H2O. And when you add H plus in there, it can add to the nitrogen and make the nitrogen a positively charged good leaving group, and you end up with the carboxylic acid. So H2OH plus works great to convert things into carboxylic acids. If we want to convert a carboxylic acid to an ester, we've already seen that one. That was the very first video in this unit, right? That was you take alcohol and H plus and you get this substitution. I'm going to leave this one blank for a little bit because that one is a little bit more tricky than we might otherwise think. And I'm going to focus on this top one. So carboxylic acid to acid chloride is actually kind of a difficult reaction because we are going uphill, right? What we have is we have a very good leaving group as our product, chlorine, and we have a very bad leaving group in OH minus as our starting material. And so we might look at this and think, well, this is impossible. But of course, anytime you tell an organic chemist that a reaction is impossible, they're going to say, well, I'm going to find a way to try and do it then. It's kind of annoying that way. And what we do is we make a leaving group as an intermediate in the reaction that's an even better leaving group than chlorine. And so let's see how that goes. So we're going to use thionyl chloride, which if you remember your organic one, you may recall we've used this trick before. This was a way that we converted alcohols, OH groups, to chlorides. And it turns out that this works as well in carboxylic acids. So it doesn't matter which oxygen we use. It's actually this one is the better one to have attack the sulfur. We attack the sulfur, we kick out a chlorine, and we get to something that looks like this. Okay. And of course, this is in equilibrium with that positive charge can be distributed not only to the carbocation, but also to this oxygen. So we also have this resonance form that looks like this. And that's why we use the carbonyl oxygen to attack there, because it leads to a more stable intermediate. All right, but if we get something like this, now what we have up here, this is a fantastic leaving group, right? So this is an even better leaving group than chlorine. Fantastic leaving group. That's the technical term for that. Okay. And so when chlorine comes in, now we also generated Cl minus up here, right? We lost a Cl minus. When that Cl minus comes in and attacks this position, right? Again, we're going to get this intermediate. And now the question is, which leaving group is going to leave, right? Every waterfall reaction that we've talked about, every carbonyl substitution reaction comes to this point where you have your nucleophile added in and you have to choose what leaving group are we going to lose. And so our choices are, we can lose OH, not a very good leaving group. We can lose chlorine, which is a very good leaving group, or we could lose this SO2Cl, which is a fantastic leaving group. And fantastic is better than very good. And so that's what's going to happen. This group is going to leave, and you're going to remake your carbonyl, and that's going to take you to your acid chloride. So we use thionyl chloride, SOCl2, as a way to kind of cheat the system. And what we do is we make an even better leaving group than chlorine, and then we use the same trick, right? Have the chlorine attack, and then we have to choose which leaving group leaves, and we lose the better leaving group in order to make our acid chloride. So we can use carboxylic acids to make acid chlorides, and this is really the only way that we use to make acid chlorides. Even in the lab, generally, if you need to make an acid chloride, what you're going to do is you're going to start with a carboxylic acid and then convert it to an acid chloride using something like thionyl chloride. There are other reagents that do this, but they all work on the same principle. So we're going to stick with thionyl chloride as our main reaction to do this, right? So thionyl chloride will convert a carboxylic acid to an acid chloride, which is very useful because that means that we can take a carboxylic acid and we can convert it into anything. We can make an acid chloride using SOCl2, and then we can go down the waterfall and make whatever we want. So if we want to make a carboxylic acid into an ester, right, we can do that directly, or we can make the acid chloride and then go onward from there. And actually, most of the time, because this reaction, the acid chloride to ester or acid chloride to amide, is such an easy reaction, like I said before, those reactions go pretty quickly. And also the thionyl chloride reaction is such an easy reaction. It takes about 10 minutes. You just dump everything together and then evaporate off your solvent and you're done. Because those two sets of reactions are so easy, instead of converting carboxylic acids directly to esters using alcohols and acid, usually what we do is we convert it to an acid chloride and then we add in whatever alcohol or amine we want and make that happen. And so this is a case where actually doing 2 steps, carboxylic acid up to acid chloride and then down to whatever we want, is actually easier than trying to do the 1 step that relies on the OH group becoming a good leaving group, because it's just not. We're almost done. One more video, I think, and we'll have it.